Hi there, and thank you so much for joining me for this video. So this video marks the beginning of our Module 9 series. And in this video series, we're going to start talking about inferential statistics. So the particular topic of this video is going to be generating, testing, and rejecting or retaining hypotheses. So before I jump into new material, I wanted to review some of the concepts that we've already talked about. So one of the first lectures that I gave in the last module, I defined for you what statistics were. So there's basically two main jobs that statistics perform, so to speak. So one of the jobs of statistics is to summarize large amounts of information or data. Okay, so these are what are called descriptive statistics, right? So the purpose of descriptive statistics is to describe or summarize a data set, right? So to tell us, for example, what the average height of people in our class is, or what percent of, so if we're looking at, for example, the percentage of our class that are sophomores, juniors, freshmen, and seniors, right? If we were to do that, one of the things that descriptive statistics could tell us is what percentage makes up the most frequent category, right, or the mode. So if 59.7% of our class was made up of juniors, then that would be the most frequent category. So all of those things fall within the umbrella of descriptive statistics. So what we're going to talk about in Module 9 and beyond is something called inferential statistics. So with inferential statistics, we are using the data that we have compiled from our sample to make inferences or answer questions about the population, right? So for example, if we were to collect information on the height of every single person enrolled in this course, what would that sample tell us about the overall distribution of heights in the entire population of Mercer students, right? So with inferential statistics, we are trying to find something out about the population using the information that we have in our sample. Okay, so again, samples and populations. A population is the group we want to know something about, and the sample is a smaller, presumably representative subset of that group. Okay, so by studying samples, our goal is to generalize what we have learned about the sample to inform something about the population. Okay, so when we want to do that, when we first want to start to learn something about the population on the basis of our sample, first we have to make a hypothesis as to how the variables that we're analyzing will be related to each other. Okay, so then we use a statistical test to decide if there is enough evidence to support our hypothesis about the potential relationship between our variables or not. Okay, so sampling error. Okay, so this is a new concept that we haven't really talked about before. Sampling error is the difference between the statistic that we calculate from our sample and the true population parameter that exists only because of observations that happen to be selected for the sample. So it's an error due to random chance. Okay? So what do I mean by that? Well, remember, we're trying to determine something about the population on the basis of our sample, right? So let's suppose we are trying to learn something about the IQ of all students currently attending Mercer, right? So maybe we stand in the quad with a clipboard and we say free IQ tests available, okay? And it just so happens that the first 10 people that agreed to take an IQ test all have IQ scores above the mean, right? So they might have an IQ score of 120, 125, 117, right? So it just so happens the people that comprised our sample tend to have higher IQs, right? Well, then our sample statistic that we calculate is going to be higher than IQs that we typically find in the population, right? So one of the ways we can avoid this problem and reduce sampling error is by increasing the sample size, okay? So the larger our sample size is, the better it's going to approximate the population. Okay, so what is a hypothesis? A hypothesis is simply a statement that outlines whatever our prediction is about either a relationship between variables or a difference between groups, right? And just like we talked about in my first lecture when we were talking about the basics of the scientific method, anytime you generate a hypothesis, that hypothesis should be informed by previous research, right? So, a good hypothesis should be complete, a complete declarative sentence that is concise. It should clearly explain what our variables are and how they'll be measured. Okay, so there should be operational definitions in there somewhere. And it should also explicitly state the predicted relationship or difference that we expect to find. Okay, so let's suppose that our research question is, we want to know if students who take an open book test will get higher scores than students who take the same test, but it's closed book. Okay, so is there any kind of conferable advantage when students take tests open book as compared to when they take them closed book, right? So in this case, rather than looking at a relationship between variables necessarily, we're going to be looking at group differences. Does the mean test score from students taking a closed book test differ significantly from the mean test score of students taking a closed book test? Okay, so let's suppose our hypothesis then is students who take an open book test will get higher scores on average than students who take the same test closed book. Okay, one thing to note is that there are different types of hypotheses. So if you specify a particular direction in your hypotheses, okay, so for example, instead of saying there will be a difference between the test scores that we obtain for open book, students taking an open book test, and students taking a closed book test, okay? If we simply stipulate that there is a difference, but we don't say which mean will be higher or lower, okay, then that's non-directional. Whereas if we say the mean or the average test score for closed book students will be greater or lesser than the average exam score for students who take a closed book test, that would be directional. Okay, so a non-directional hypothesis predicts a relationship or group difference, but does not specify the nature of that difference or the direction, whether it's positive or negative, right? Or higher or lower. Okay, so for example, the average test score of open book students will be different from the average test score of closed book students. Okay? Whereas directional hypotheses state the direction, which one will be bigger than the other. Okay? So open book students will get higher scores than closed book students, or the opposite of that. They'll get lower scores. Okay, so in this example, okay, we need to pull some information out before we go forward. Okay, so looking at our research question and our hypotheses, we first need to determine what our independent variable is and what those levels are and what our dependent variable is. Okay, and because we now have more information, thanks to our last module about the type of variables that we have, we need to stipulate whether they're categorical or continuous. Okay, so think about that for a moment. What is our independent variable? What is our dependent variable? How are they measured? And are they categorical or continuous, right? Each of our two variables, our IV and DV, are they categorical or continuous? Okay, well, our independent variable is testing condition, and the two levels are open book or closed book, okay? So this is a categorical variable with two groups, and it's also a nominal variable because the only information we're getting from this variable is name, essentially. Okay, so we have a name for the levels, but there's no order of magnitude. There's no sort of quantitative component here, so it's a nominal variable. Okay? As opposed to our dependent variable, which is test score, okay, that is inherently quantitative, so it's a continuous variable, okay? And again, when we stipulate our hypotheses, we can predict a relationship between the variables. So we can again say there will be a relationship between test condition and test score, or we can predict a specific difference between groups, okay? There will be a difference in test scores between the open book group and the closed book group, and that would be a non-directional hypothesis. Okay, so at the outset, we have differentiated between a directional and a non-directional hypotheses. Okay, now we're going to talk about another grouping, if you will, or difference between hypotheses. So the null hypothesis always stipulates that there is no relationship or difference between our variables. Okay? So whenever we begin our study, our assumption at the outset by default is that if the null hypothesis, abbreviated H sub O, is true, there is no relationship or difference. Okay, so when we begin our study, we assume by default that there is no relationship or difference between our variables. Okay, if we find weak evidence of a relationship or difference after we collect our data, then we retain the null hypothesis. Okay? And if we find evidence, strong evidence of a relationship or difference, we reject the null hypothesis. Okay? Okay? So in our case, we assume at the outset that there is no relationship between testing condition and the test scores we obtain. Right? So in other words, the null hypothesis says that the average test scores of open book students and closed book students will not be different from each other. Okay? So if the null hypothesis says that there is no effect or relationship, then the goal of our research is to attempt to find evidence that the null hypothesis is wrong and that our hypothesis is correct. Okay? So the alternative hypothesis, abbreviated H sub A, is our prediction of the relationship or difference that we expect to find, right? And it's essentially the exact opposite of what's being posited with the null hypothesis. Okay? So again, in our example, we are positing that there is a relationship between testing condition and test score, okay? Or we're saying that the average test scores of open book students and closed book students will be different from each other. Okay? So every time we run a statistical test, what we have to decide is, are the results that we obtain due to random chance or sampling error? Okay? Or is there really a relationship or difference? Okay? Okay, so again, just to put everything together, our research question is, do open book students get higher test scores than closed book students? Our null hypothesis, or the hypothesis that we are testing every time we conduct a statistical test, is open book and closed book students will get equivalent test scores, or the test scores obtained from closed book and open book students will not be different from each other. In contrast, the alternative hypothesis, also known as the researcher's hypothesis, is that open book students will get higher scores than closed book students. And again, this is a directional hypothesis. Okay, so after we have solidified our research question and stated both the null hypothesis and the alternative hypothesis, our next step is to actually collect data from our sample. Okay, so we randomly assign some participants to each group, and then we give them the open book or closed book test, and then we run a statistical test that compares the data from each of those two groups to determine if they are different from each other or not. If the statistical test reveals strong evidence for an effect or difference, then we reject the null hypothesis and we conclude that there is a relationship between testing condition and test score. If the evidence we obtain from the statistical test is weak, okay, then we retain the null hypothesis and assume that we don't have strong enough evidence to support our hypothesis that there is a relationship. Okay, so we don't have enough evidence to support the hypothesis that that closed book students differ significantly from open book students in terms of their test score. Okay, but how exactly do we make this decision? So what constitutes strong evidence versus weak evidence? Okay, well, what statistical tests tell us is they tell us the probability of getting a particular pattern of results assuming the null hypothesis were true, right? So essentially what a given statistical test tells us is the probability of getting these same results from our sample if the null hypothesis were true and there was actually no difference. Okay? Okay. So if the probability of getting the same results if the null hypothesis were true and there was actually no relationship or no difference is high, okay? And we consider anything over 5% to be high, okay? Then we attribute our results to sampling error, okay? So we assumed there was something about our particular sample that meant that it does not really approximate the population, okay? So there was something specific about our sample that meant it was an incorrect approximation of the population, okay? So in other words, we don't have good enough evidence that the null hypothesis isn't true, okay? So we retain the null hypothesis and reject the alternative hypothesis, okay? Okay, if the probability of obtaining the same results if the null hypothesis were true, okay, is less than 5%, then we have good evidence that the null hypothesis isn't true, so we reject the null hypothesis in favor of the alternative hypothesis, okay? So if the probability of observing this same difference or this same relationship, if the null hypothesis were true, and in fact there was no difference, is low or less than 5%, then we have strong evidence that we can reject the null hypothesis in favor of our hypothesis, the researcher's hypothesis or the alternative hypothesis. Okay? So getting these results is very unlikely if the null hypothesis were true and there's actually no difference. Therefore, the null hypothesis probably isn't true. Okay? So it's essentially saying there is not no effect. Okay, so we are essentially rejecting the claim that there is no difference in favor of our hypothesis that there is. Okay, so one of the terms that I'm sure you guys have heard, certainly in reading research articles and things like that, is statistically significant. So what does significant mean in this context? Well, in statistics, significant means that our results are very unlikely to have happened by chance, or another way of saying that is our results are very unlikely to have happened due to sampling error. Okay, so a significant results means that your results are so unlikely to have happened just by random chance that you can say there is a difference or that there's a relationship. So the cutoff that determines whether you have strong evidence in favor of the alternative hypothesis or weak evidence in favor of the alternative hypothesis, okay, is less than 5%, okay? So this cutoff of less than 5% is called the alpha level. Okay? So every time we run a statistical test, we will get a p-value, which is also known as an alpha level. Okay? If our p-value is less than 0.05 or less than 5%, then that means that our result is significant and that we can reject the null hypothesis, right? So there is a less than 5% chance that we would obtain these same results or that we would observe the same group differences if the null hypothesis were true, okay? So because there's a less than 5% chance of observing the same results if the null hypothesis were true, we can reject the null hypothesis, okay? If the p-value is bigger than 0.05 or bigger than 5%, okay, then that's weak evidence in favor of the alternative hypothesis, okay? And we would say that there is not enough evidence to conclude that there is a significant difference or that there is a difference between our groups or there is a relationship between our variables, okay? So if we get a value, a p-value greater than 0.05 or greater than 5%, that means that there's a greater than 5% probability that we would obtain the same results from our sample if the null hypothesis were actually true, okay, and there was no difference. So if the probability is greater or the p-value is greater than 5%, we conclude that this difference that we've obtained is due to sampling error rather than a true group difference in the population. Okay, so we conclude there was something weird about our sample, something weird about the participants we collected data from, and that our sample is therefore not representative of the population. So we attribute this difference to our strange sample or just random chance rather than reflecting a true difference in the population. Okay, so one thing to note is that when we use the word significant in statistics, it has nothing to do with the relative importance of the finding, right? So significant doesn't mean it's important, okay? But rather it just means if the null hypothesis is true, we would get these results less than 5% of the time. So therefore, we conclude that these results are not due to chance, and we can accept our alternative hypothesis that there is truly a relationship or a difference between these variables in the population. Okay, so again, just to recap, whenever we conduct a statistical test, we are trying to determine whether the evidence against the null hypothesis is weak or strong, okay? And our indice of whether the evidence in favor of the null hypothesis is weak or strong is going to be our p-value or our alpha level. Okay, so if our result has a p-value greater than 0.05, what this means is that we would obtain the same results more than 5% of the time if the null hypothesis were true. Okay, so therefore we are not confident that the null hypothesis is false. Okay, and therefore we retain it and conclude that there is not a significant relationship between our variables or a significant difference between our groups. Okay, if the p level, also known as the alpha level, is less than 0.05, that means that there is a less than 5% chance that we would obtain the same result, or that we would obtain the same relationship or group difference if the null hypothesis were true. Okay, so there's a less than 5% chance that we would get these results if the null hypothesis were true. Okay, therefore, the evidence against the null hypothesis and in favor of the alternative hypothesis is strong. Okay, so therefore we reject the null hypothesis and conclude that the observed difference or relationship in our sample is significant. Okay. Okay, so our magic number or cutoff point is our p-value or our alpha level of 0.05, right, or 5%. So if our p-value is above 0.05, then we can conclude that the difference we observe between groups, or that relationship that we see between variables, is reflective of sampling error. And therefore, because it's due to random chance alone, we have weak evidence against the null hypothesis, and therefore we have to retain the null hypothesis. Whereas if our obtained value is less than 0.05, if our p-value is less than 0.05, then that means we can be confident that the difference or relationship that we've observed is reflective of a true difference in the population, right? But there's always the possibility that either way, whether we reject or retain the null hypothesis, we might be incorrect, right? So basically, if our value is 0.05 or higher, what that means in effect is there is a 95% chance that the difference in our group, between our groups, or the relationship between our variables does exist in the population, right? But there's also a 5% chance that the difference we've observed is not due to a true difference. It's due to sampling error, right? And conversely, if our p-value is above 0.05, okay, if it's greater than 5%, and we decide to retain the null hypothesis, okay, and assume that there is no difference in the population, okay, what that means is that there's a 95% chance that there is no difference in the population, but there's a 5% chance that actually there is, and the results we obtained were not due to sampling error, right? So let's talk about those types of errors, okay? So what I have plotted on this table for you at the top is what we decide, okay? So we answer the question, is there actually an effect or relationship? Okay, so what we do is up at the top, or excuse me, okay, so in the left-hand column is what we decide, right? So do we conclude that there is an effect or relationship? That's plotted on the side. And is there actually an effect or relationship in the population? That is plotted on top, okay? And this will make more sense in just a second. Okay, so let's suppose that we conclude that there is no relationship between testing score and testing condition, or there is no difference between the average test score of open book students and the average test score of closed book students, right? So we conclude that there is no relationship or difference when in fact, in actuality, there is no relationship or difference, okay? That's not an error, right? That's a good outcome. Okay. Similarly, if we conclude that there is an effect or relationship, so there is a difference between open book and closed book students, right? When in fact there is a difference in the population, good. That's not an error, right? We rejected the null hypothesis and assumed there was a difference when in fact there is, right? So those are not errors. Those are the ideal situations. But let's suppose that there is actually an effect or relationship, but we conclude that there is no relationship. Okay, so let's suppose that we have strong enough evidence to reject the null hypothesis, but instead we choose to retain it, right? Well, that's considered a type 2 error, right? And type 2 errors occur when we incorrectly conclude that there is not a relationship, but there actually is one, right? So said differently, we conclude that the difference we observe is reflective of sampling error and not a true effect or a significant effect, and we reject or we retain the null hypothesis, when in actuality there is a true difference in the population. Okay, so in effect, again, we conclude there is no relationship between testing score and testing condition when in fact there is. That's a type 2 error. And lastly, we come to type 1 errors, right? So a type 1 error occurs when we conclude that there is a relationship when in fact there is not one. Okay, so said differently, a type 1 error occurs when we assume that the null hypothesis is wrong, okay, or we reject the null hypothesis when in fact the null hypothesis is true. Okay, so we conclude that there is a relationship between testing condition and test score, but there really isn't a relationship. Okay, so we conclude that our difference that we observe in our sample is reflective of a difference in the population when in fact it is due to sampling error. Okay, so that is considered a type 1 error when we reject the null hypothesis when in fact the null hypothesis is true. Okay, so let's kind of sum things up if we can here. Okay, So our research question was, do open book students get higher scores than closed book students? Okay, so that's our research question. And our research hypothesis or alternative hypothesis is that there is a relationship between testing condition and test score, and that the average test score for open book students will be higher than the average test score for closed book students. Okay. The null hypothesis is that there is no relationship between testing condition and test score, or that the average test score for open book students will be no different than the average test score for closed book students. Okay? So we run a statistical test, and the p-value or alpha level after we run the statistical test. Okay, let's say that that p-value is greater than 0.05. Okay, then assuming the null hypothesis is true, the probability of getting these results by chance or due to sampling error is greater than 5%. Therefore, we conclude that there is actually no relationship between testing condition and test score, or that there is no difference between the average test score of open book students and closed book students. And therefore, we correctly retain the null hypothesis, right? Or, in fact, there is a difference in the population, okay? And there is a relationship between testing condition and test score, but we reject the research hypothesis and retain the null hypothesis, okay? So there are two possibilities if we were to observe an alpha level greater than 5% or above 0.5. Okay, one possibility is that we retain the null hypothesis correctly, and there's in fact no difference or no relationship between testing condition and test score. And another possibility is that we've committed a type 2 error. And in fact, the difference we observe in our sample, or the relationship we observe in our sample, is a true relationship that's reflected in the population, but we have assumed that incorrectly that the null hypothesis is true. Okay, similarly, if we observe a p-value of less than 0.05, right, then we assume that if the null hypothesis is true, the probability of getting these results by chance or due to sampling error is less than 5%. Okay, and if the probability of getting these results by chance or sampling error is less than 5%, then we conclude that there is a relationship between testing condition and test score. Okay, and there's two possibilities. One is that we have correctly rejected the null hypothesis in favor of our research hypothesis. Okay, or there's a possibility that we have committed a type 1 error. Right? So again, a type 1 error occurs when we reject the null hypothesis and assume that the difference that we've observed between our groups is a true difference that's reflected in the population, okay, when in fact that difference is due to sampling error, okay, rather than a true difference in the population. Okay, so a type 1 error occurs when we incorrectly reject the null hypothesis in favor of the research hypothesis. Okay, so again, a type 2 error occurs when we incorrectly retain the null hypothesis when there is actually a difference in the population. And a type 1 error occurs when we incorrectly reject the null hypothesis when in actuality there is not a relationship or difference in the population. Okay, so I know this was a lot of information, and hopefully you'll be able to apply a lot of these ideas when you check out my next video in Module 9. But certainly if you have any questions, don't hesitate to reach out, and I look forward to seeing you all soon.